I will continue. Thank you for bearing with the solar wind associated talks. So this is also a little bit more like Milan's talk, a little more geared to particle distribution functions than the fluctuation side of it, but I'll talk about that a little bit as well. Just a little bit of an overview. So what I want to really give you a flavor for is ways we can use the solar wind as a laboratory for plasma dynamics. In particular, I'm going to show you examples of how we take advantage of the fact that the solar wind, mainly I'll show you data from 1AU, tends to range from 10 to the minus 2 beta to beta of 100. So we can explore how the dynamics change as a function of beta across beta of unity. Same thing happens in the ratio of collision to dynamic timescales. We cross unity. So the solar wind's a very useful laboratory for studying how, when we can describe these plasmas using fluid MHD, when more of a kinetic description is required. I'm going to try and, I put in as many examples as I could of different things we observed just to stimulate everyone, show you some hopefully puzzling examples of things we don't have explanations for, where it kind of acts half like a fluid and half like a set of non-interacting particles. And the main examples I'll be showing you: instabilities, ion heating, and then a little bit of work we've started doing on ion-electron interactions. Please feel free to interrupt me if you have any questions. So once again, I'm talking about plasmas in the heliosphere. I think you've already seen a few reviews of heliospheric structure, solar wind, the corona, so I won't go into detail again. I do want to just set this in a context everyone in this room is familiar with. So our minor radius is 1AU. Put it in a tokamak perspective. Okay, so just to remind you, the corona is not in hydrostatic equilibrium. You have a lot of structure. So when you look at the solar wind, you have streams that are high density, low density, fast, slow. There are eruptions and shocks. The plasma is hotter or cooler, so there's a lot going on. Now in interplanetary space, our spacecraft are a lot smaller than the Debye length, and that's why our ion instruments are able to measure the velocity distribution function so well. We can't prepare shots the same way you guys do. But what I like to do is think of the solar wind as kind of an ergodic system, where if I can get some instruments up there and just wait long enough, it's going to eventually explore all the possible configurations that it can. Now, it's not a truly ergodic system, in that some irreversible stuff happens if you happen to venture into particular ranges in phase space, and I'll be showing you some of that. But our starting point is, at this point now, a very massive database of the different plasma conditions that we can access. So we have a fleet of spacecraft that explore the heliosphere. This is a snapshot of our capabilities from a few years ago, and as Tim pointed out on the first day, we can't really claim that we planned on building this heliospheric observatory from scratch. And unfortunately, one issue you'll have is one spacecraft will have like the best electric field sensor you could possibly want. Unfortunately, that's not the same spacecraft that has the really good ion measurements. But there's a very nice spacecraft called WIND, which right now sits at the first Lagrangian point, about 1% of the way back towards the sun. WIND was launched in 1994, and it will be the basis of a lot of the data that I show you. And the nice thing about WIND was this spacecraft was just bristling with instruments, very capable instruments, a lot of redundancies. So you've heard a couple times Stuart talked about 3DP instruments, solar wind measurements. So you have multiple instruments measuring similar quantities, which is really nice when you're trying to make sure you understand everything.
That plot makes us feel very good in the fusion business. We're not as bad as we thought we were with acronyms.
Oh yeah, don't get us started, right?
But we are less bristling with instruments. Wow.
Well, you make measurements at more points. I think. Yeah, I'll try to keep the acronyms to a minimum. If I start going off the deep end, rein me back in.
Mars in the foreground.
Oh yeah. Well, you know, we will. We're being filmed live. We attempt to demonstrate our relevance to the pressing national interests of the time. All right. So WIND was launched in '94. It's still operating. It's about yay big. It spins once every 3 seconds, as you've heard. Its booms are about, is it 100 meters tip to tip?
Yeah, 100 meters and then 30 meters.
Yeah, so think about this thing. It's in space, it's spinning once every 3 seconds. The tips of those electric field probes are moving at a couple hundred meters per second. It's nice to be in a vacuum. The goal of wind was to understand solar wind upstream of Earth. We had a lot of extra fuel, so it's been really fun working on wind. You'd have a team meeting and we'd say, well, where should we go now? Let's go by the moon again. That was kind of fun. Let's go to the second Lagrangian point behind Earth and see if things are very different. Lately, though, we've just been parked at L1 in a nice little stable halo orbit. That's good for us because it basically means the last 5 years or so, just contiguous solar wind sampling. And at this point now, we have a very excellent complement of stable, accurate, very well understood instruments. For the ions and electrons, we've assembled more than 5.3 million shots, like snapshots of the velocity distribution functions. At the same time, just hundreds of associated parameters about electromagnetic fluctuations, energetic particle states, yada, yada, yada. Okay, so what I'm interested in is the kinetic physics of the solar wind. And the very earliest solar wind measurements we had showed that ion and electron VDFs, the phase space density, are almost but not quite Maxwellian. So a very simple question we can do in the solar wind is what keeps them from being Maxwellian? I think you've seen something like this a few times now. Here we have Helios measurements at 0.29 AU, fast solar wind. The magnetic field is on this dashed line. We have a very anisotropic proton distribution function, little proton beam there. So what's keeping them from being Maxwellian? Well, they're very low densities and very high temperatures. At 1 AU, a typical proton experiences 1 weak Coulomb scattering per AU it travels. So Coulomb collisions are very infrequent. Baryonic collisions maybe happened once a billion years ago. So interactions between electromagnetic fields and particles of a particular speed is kind of the dominant process in the collisionless solar wind, not it acting as a collisionally coupled fluid. And one way you can see this that I'll be talking about in detail today, you look at the ratio, for instance, of the alpha particle to proton temperature. Protons, hydrogen and helium, are fully ionized in the solar wind, so I'll interchangeably refer to them as alphas and protons. And what you see is this is a histogram of several million measurements of the alpha to proton temperature ratio. There's a very strong peak at 1, equal temperature. That makes sense. There's a second peak at a temperature ratio of 4, and so that's equal thermal speeds. So just hand waving, that should be evocative of the fact that I have waves that are traveling through this plasma, and it's picking up particles moving at a particular speed, and it's giving them equal thermal speeds. But let me also point out that 22% of the data shaded here in gray exceed this simple, actually that's a temperature ratio of 5 and higher is 22%. And that doesn't even fit in this simple equal thermal speed. This is supramass proportional heating, and it's something I'll be discussing today. Well, if all this is going on, why are they even close to Maxwellian? Right? And so that's the other side of this, and that's this kinetic physics of the solar wind. When and where is MHD valid? When do we need to include details of the velocity distribution function? How many details do we need? Is being a bi-Maxwellian sufficient? Is gyrotropy always sufficient? If we could look closely enough, do we need to actually see what the phase dependence is when we really look at dissipation? Right? And what are the signatures in the velocity distribution functions of many different interesting processes? Okay, so now I'm just going to walk through a whole bunch of topics. We'll see how many I get through. And the first thing I want to talk about is collisional relaxation in the solar wind. So to pick a victim, Tim, on Monday, stood up and showed this plot.
Nope.
Yes, you did. Didn't you? Okay, you showed 4 of them. Yeah.
You should have showed.
You should have showed this one. So this is in our field.
Remember it.
This is in our field a canonical figure. It's 9 Helios measurements of the velocity distribution function of protons at 1 AU, and then at half an AU, and then at 0.3 AU, and then for slow wind, intermediate, and fast wind. And what we get out of this is the closer you get to the sun, in particular for fast solar wind, here's where you get these weird things. You get bi-Maxwellian distribution functions. Those are also protons, so there's 2 peaks in the proton distribution when you get close to the sun in the fast wind. So you have all these different kinetic or non-thermal features, field line anisotropies, beams, different temperatures. It's stronger closer to the sun, it's stronger in fast wind. And in our community, we have this paradigm that slow wind is Maxwellian and behaves like a single fluid. Fast wind has strong non-thermal aspects, so slow, fluid, fast, kinetic. And we think that might have a lot to do with the origin of the wind, that maybe, fast wind, because there are actually problems. The fast wind has way too much momentum flux to be explained by simple solar wind models. There has to be some additional oomph imparted in the fast wind as it comes out. And we think that maybe these, in the standard picture, these non-thermal features are indicative of the processes that happen closer into the sun to give us the fast wind. Another way to look at this with these large data sets is let's pick a few kinetic properties and let's see how they depend on solar wind speed. So we'll look at the alpha to proton temperature ratio, the proton temperature anisotropy, and differential flow between alphas and protons. I'm going to normalize that by the alphane speed because, as I've said, that ratio rarely exceeds 1 in the solar wind. But as long as you're below 1, the minor ions seem to be perfectly free to just slide along the local magnetic field relative to the protons. And indeed, you see, when you look at slow solar wind, you have simple temperatures, anisotropy, I don't know if there's a particularly clear trend, small differential flows. You go up to faster wind speeds, here's where you get the large differential flow, here's where you get the high temperature ratios. So there's clearly some dependence, but why are we sorting by speed? That's not a particularly dimensionless quantity. So we should consider a thermalization timescale instead. And we've had a couple people now this week point out this Coulomb collisional age. So just the product of the 1 over the time it takes you to get to the spacecraft from the sun, and the Coulomb collision frequency, which I have not written out, but is proportional to density over temperature to the 3/2. Cute thing about the solar wind is density and temperature conspire radially as they evolve from the sun to give you a relatively constant Coulomb collision frequency. So you're sitting there asking yourself, why are these people taking the collision frequency at one distance from the sun and thinking that's at all indicative of the historical collision frequency? And I'll just say it's not as bad as you think. Let me remind you, the fast solar wind gets to you quicker, so there's less time for there to be collisions, right? But it's also hotter and less dense. So you might expect that fast wind tends to have a very low collisional age. And in fact, previous work has shown that it's when you have large collisional age, you tend to have smaller differential flow and equal temperatures. And let me also point out, solar wind speeds vary by like a factor of 3. This collisional age spans like more than 4 orders of magnitude. So again, it's a nice parameter for us to study. So here on the left, I have the one data set sorted by solar wind speed. And here on the right, I have the exact same set of measurements, but now sorted by the collisional age. And this is a stunning transformation. All our parameters are now very simple monotonic functions, very clearly ordered by the Coulomb collisional age. So, I hope that you're sitting here thinking he's kind of stating the obvious. It's surprising how many insights are sitting in these data that we're only just recently beginning to appreciate. I think that this tells us that there's a clear transition in the kinetic dynamics of our solar wind. Note the actual values here. The transition happens for an age of between 10 to the minus 1 and 1. So only 1 Coulomb collision per particle on average seems to be sufficient to start washing away the non-thermal features that are injected closer to the sun, or that are generated locally.
190-degree collision.
Excuse me?
190-degree.
A super extremely weak collision. Grazing incidence, it's just Spitzer collision frequencies.
It's new, so it's basically 1 exponentiation, right? That's what we usually assume, that you need 1 collision target before you establish the Maxwellian.
So one collision time is many grazing collisions.
Yes.
190-degree collision.
That's right.
Yeah.
Equivalent.
Justin, can I ask a question about the second panel on that right-hand figure?
Don't ask about the second panel.
Why do you think that?
I don't know.
Why does it minimize that? Why does T-prop over T-parallel sort of appear to minimize there?
Like come back down? Yeah, I really don't know. I mean, I think it's because there are multiple things happening. Right. So if there were fewer collisions, you'd have double adiabatic expansion that would pull you down. But then that roll-up might have something to do with the fact that this is preferentially fast solar wind, where T-perp tends to be a little larger. But I'm not sure. It's a very good question.
Also, it seems that there is a bit maybe clear maximum in the ratio of T or TP.
Yeah, yeah. You mean like here?
Yeah.
Yeah. Yeah, that's true.
You're right, and there's distance effects rolling as well. I mean, in an ideal world, you do this at several distances.
Yes. I would love to have all the Helios data.
Well, but that's sort of the point. I mean, this is a dimensionless. This is a dimensionless.
Quantity.
So it's.
Yeah. No, I'm very keen to.
Physics, not the
Yep.
position that it is.
Yep. Or at least it'll be nice to verify that. Okay, so collisions actually important from time to time, and we can study that in the solar wind. Let me now move on to that second panel that Stuart pointed to and talk about proton temperature anisotropy. So what regulates temperature anisotropy in the solar wind? First order, we've got double adiabatic expansion. So T-perp is going to, for an adiabatic transformation, T-perp will vary proportionally to B. T-parallel will vary as n squared over B squared. So when we talk about our anisotropies, T-perp over T-parallel, you might, to first order, expect them to just respond as B cubed over n squared to a sudden adiabatic transformation. So when you ask what happens as the solar wind expands, you need to ask yourself, how do B and n vary with distance from the sun? Remember, in the solar wind, B does not fall off as 1 over r squared because of the Parker spiral and the orientation of the magnetic field. So the rate at which these anisotropies would change from CGL is actually a function of the geometry of the magnetic field and how far away you are from the sun. Now, when I read this in physics class, I thought, okay, sure, adiabatic transformations. Is this really ever valid? I know you can have, in thermodynamics, you spray your shaving cream can and it gets cold. So, okay, I see how this is valid in some situations. But is a double adiabatic equation of state really valid in the solar wind? And there's a very nice case published by Clackenall in 2003 that's like a textbook, let's fire the piston and see what happens case to test this. So what happens is you have the moon, which is just a perfect insulator, and so the solar wind flows past it. In this case, the sun was in this direction, the solar wind was flowing at this angle, and the wind spacecraft zipped through the cavity created behind the moon. And in the lunar wake, in this lunar cavity, what happens is electrons zip in immediately. They're moving a lot faster than the protons. And they yank the protons and they pull them in to fill this wake. So when you sit here a couple lunar radii behind the moon and fly through this wake, the plasma has had milliseconds to flow into this wake and respond. And so what we did was we fly through, and I'm not going to get into too many details of the wake. Let me just say, here's the density of protons coming into the wake. The time we're in the wake is this red region, all right? And you can see there's solid circles and then there are open circles. And so what happens is there's a magnetic field, all right? And so the electrons come streaming in, they create an electric field, the protons want to come flying in, but they're constrained to move along the magnetic field. So they flow into the wake from two directions, in two directions only. And when our spacecraft goes in, we see two beams interpenetrating of protons. And so what you're seeing here are the densities of the two different beams. So you start out with a very high density and then it falls off as you enter the wake, but you start picking up the beam coming in from the other side and it comes up.
How wide is the wake? Thousands of kilometers?
Thousands of kilometers. So a few proton gyroradii, several, close to the moon. And so here, on this panel is T-perp over T-parallel for those two proton beams, looking at them independently. And what you can see is for both of the beams, T-perp over T-parallel got up to about 10 or so, which is larger than we ever really see it in the solar wind. So the first time we saw this, we were very excited. Aha, we've discovered evidence of the heating process that heats the solar wind. But then we realized, a millisecond really isn't enough time for these things to develop. But the gyro period is a second out here. So we really doubted the protons were absorbing waves in a thousandth of a gyro period. But then you take the ratio of B cubed over n squared, and that's this solid line. Right? What you find is that the wiggles and the change in the temperature anisotropy are predicted very precisely, just assuming double adiabatic expansion into the lunar wake. So here's a nice little textbook example where we can look at this plasma quickly flowing into the wake cavity, and you develop large perpendicular anisotropies in this case because of how V and N vary. and it's very well described by CGL. So I just thought I'd show that as a little textbook example of the validity of the double adiabatic equations under some cases. Question?
I'm confused. You said this happens fast compared to this proton-cyclotron frequency?
Yes.
On that scale, double adiabatic laws is not valid.
Let me point out another problem with this, since you raise it. How come the beams independently know to transform according to the double adiabatic predictions, even though the double adiabatic equation is really for the total pressure, perpendicular and parallel? So there are a bunch of contradictions in this data set.
What's the curve for adiabatic?
But twice you said this is happening on milliseconds, but the convection time from the moon to where wind is going to be tens of seconds more than that. Yeah. So if you look at that, so a lunar radius is what, 1,600 or something kilometers? Something like that?
Yeah, okay, it could be
And
tens of
you're-
seconds.
You're 20 lunar radii downstream, and you're only doing a few hundred kilometers a second. So
It's true.
tens of
It could be
seconds.
tens of seconds. That's true.
So it's gyro periods, as opposed
It's not
to
a sub-gyro period. That's true. The plasma coming in right at the edge experiences this rather violently.
Yeah.
But that's true. When you're out,
Yeah.
by the time you're out here, it's had tens of seconds. But I've always been stumped by the fact that the two individual beams each know how to respond to the change in the total number density, and not their individual number density.
Every particle individually satisfies this law just from mu conservation. So it's fine that they're two independent strings.
But they know what the total density is.
Yeah.
in other field.
Yeah, they know the fields.
They know the field, so
Yeah.
it's only conservation, a consequence of mu conservation.
Yeah. Okay, so let me talk about other effects. Coulomb relaxation, which we've talked about a lot now, and then instabilities, which people have also brought up. So for T parallel greater than T perpendicular, you have the fire hose instability. There's a little functional form for it that people tend to use, some exponent for beta. And then for the cyclotron and mirror instability, again, there's a bit of a functional form. Now, we keep in all these plots showing like keep out zones. And let me just point out what we mean by that. What we do when we calculate these curves is we say, okay, I'm going to use some technique, say linear analysis, with some number of assumptions about the distribution functions. And I'm going to make the distribution slightly anisotropic. And I'm going to ask myself what the growth rate is. And then I'll step through phase space in our examples in the anisotropy beta plane, and I'll say, where's the contour where I have a fixed growth rate for this instability? 1,000th of the cyclotron frequency, 100th of the cyclotron frequency. Those are the contours that we then show. And so our hand waving is, well, as I go further past those curves, the growth rate of the instability will skyrocket, and therefore there's sort of an effective force pushing me back away from those regions. So I might expect the data to order themselves along those contours. But predicting exactly how quickly we expect the plasma to fall off in occurrence across those contours is still an open issue. All right, so when I say instability limit, I don't mean binary 0 or 1, you can be here, you can't be here. I just mean the instability is going to start growing more strongly once we cross that threshold. All right. And there's another general process that could change our temperature anisotropy, and that's, I'll call it cyclotron resonant heating. There are a lot of theories that could give you preferential perpendicular heating. A lot of work goes into perpendicular heating in the solar wind, in part because from spectroscopy of the solar corona, we can see that minor ions, such as oxygen and iron and carbon, have temperature anisotropies of T perp over T parallel of 10 to 1, 20 to 1, maybe 50 to 1 in some cases. So we think one of the signatures in the plasma of the anomalously high heating in the corona are very large perpendicular temperature anisotropies. And there's other evidence that perpendicular heating happens. All right, so you could have something, maybe cyclotron resonant heating driving T perp over T parallel up. So now if I plot anisotropy versus plasma beta, and just to be clear, we're all showing the parallel proton plasma beta in these plots. Here's your sort of stable space bounded by these instabilities. Fire hose instability only is effective for beta greater than 1. And then you might have Coulomb collisions, relaxing your plasma so it becomes isotropic. cyclotron resonant heating pushing upwards. And when we look at the solar wind, it's some nightmarish combination of all these processes happening simultaneously. So this was the first attempt to look at the distribution of anisotropies as a function of beta. This was published back in 2003. Indeed, you can see these are logarithmic contours. So the distribution is sharply peaked at a beta of around 0.8 or so and an anisotropy of around 0.8. But we have a very broad range that we can study. And as you get to higher beta, you can see there's this sharp constraint. All right, so Stuart already showed this. I won't get into too much detail. The cool thing first was we were able to take everyone who'd written about these instabilities has predicted values for these exponents going back to the original predictions for the mirror instability by Chandrasekhar, Gene Parker's predictions for the fire hose instability, and then with time advancing from the MHD predictions to linearized Vlasov predictions, hybrid codes, particle and cell codes, and then finally some initial observations. And what we're able to do is we can look at the functional shape of these of the observed limit and compare it with the predicted curves and see what agrees better. So you've seen this a few times. I just want to point out some things. So cyclotron instability growth curves, mirror instability growth curves. The blue contours are the exact same data set. We're just comparing different growth rates. And here we have the standard MHD parallel fire hose. Here we have an oblique fire hose. And so what you can see is the mirror instability and the oblique fire hose fit the functional form of the data better than the cyclotron and the parallel fire hose instability thresholds. And this is a problem, because if you look in our literature at least, everyone says that T-perp over T-parallel is limited by cyclotron instability for beta less than around unity. So our data have no business lining up well with the mirror instability threshold. Furthermore, if you do linear analysis of the oblique fire hose instability, its growth rate is significantly slower than the growth rate for the parallel fire hose instability. When I first saw the papers calculating oblique fire hose phenomena, I just rolled my eyes, like,
What do you mean by that? Do you mean parallel means K-perp equals to 0 and oblique
Yes.
perp not equals
yes, and it can take on any angle.
Oblique's faster than parallel.
It scatters more effectively, but its growth rate is not faster.
Fire hose has a max
Electrons, but the protons is the other way around.
No, we're talking
This is protons.
Yeah, I'm talking about protons. The peak fire hose growth rate is at K-perp squared over K-parallel squared.
I think for protons that's not the case.
Look at these are the growth rate contours. So you can directly
you can
compare.
see that.
How about phase speed? What is phase speed? What's the difference between parallel and oblique? Here's the threshold. Sorry?
I have no idea.
I mean, that might have part.
That may be it.
That may be it. So,
It's not propagating, it just may hang around longer.
well, that's exactly it. So we think the oblique. Okay, now modulo you not believing what I'm saying.
The parallel does propagate when you get to
Right.
close enough.
Yes.
The question is, what does oblique do?
Yes.
It's the same. Oh no, they both propagate. Everything propagates.
The oblique
I mean, I
one
always
is
thought
not
that's why the mirror is.
Yeah, likewise.
One is not propagating.
Ever.
Weakly.
So I make K-perp arbitrarily small and it doesn't propagate, and when it's 0 it propagates. You're saying if I make K-perp 0 it'll propagate, and if I make K-perp arbitrarily small it doesn't propagate.
In the fastest growing mode.
The fastest growing mode is not infinitesimally close to
Well,
being
you
a
just
parallel
told me
wave.
The oblique fire hose is not the fastest growing mode at all.
No, we said the oblique is the faster growing mode. You're saying the oblique. Ah, sorry.
No,
Yes.
I'm saying
when
the
you
oblique
when
is
you
the fastest growing mode, and it propagates.
yeah, the fat of let's see.
But I may be wrong.
Yeah.
It's certainly on the other side of the curve. That's always been my interpretation of the mirror because it's non-propagating. It hangs around longer, so it isotropizes better.
This is our take.
What you observe in simulation is that if you enter in the unstable region, you first excite the parallel one, so you first observe parallel waves. But if they are not able to stop the growth of the anisotropy, you will develop also an oblique one. And this can be more effective on reducing the anisotropy, and so you can observe both, and so a mixed spectrum.
So this is part of what I'm trying to get at. What surprised me about these data is there are very different predictions coming out of linear code versus hybrid simulations where we look at the time evolution. And in the hybrid simulations, you see the parallel fire hose, well, what Lorenzo just said, I won't repeat it. But so that's been very interesting for us, because we'd originally just started assuming the cyclotron and the parallel fire hose were the right way to describe the bounds. But it appears that if you do time-dependent simulations, you actually watch the wave-particle interactions develop, that the mirror and the oblique fire hose seem to do a better job at constraining the data.
But that plot does not show that.
Yes, very good. We will
Because
continue.
It shows that the mirror fits better than the cyclotron, but it doesn't
The other
show
ones
that
are
oblique fire hose fits better than parallel fire.
Yeah, I
They're
would
almost exactly the same place.
I would agree with that. I would agree with that. It's the mirror cyclotron I think is the far better case here. But so I'm intrigued to see your guys' interaction about the top of the plot too, because if you point this out in a solar wind conference, people start hissing and booing. They're like, no, cyclotron instability is the only important thing for beta less than 1. So
what happens along that growth, that mirror growth rate when you get to beta less than 1?
you mean in the
Does the mirror
simulations?
grow
or-
for beta less than 1?
I don't know. Lorenzo, can you even see it?
It's not compressive.
I didn't.
I mean, so if you follow those marginal stability curves of the mirror instability.
When you've done PIC
Yeah,
simulations
but
up
it
here.
does grow because these are the marginal stability curves, so above them.
Yeah, I guess that's right. That's the answer, isn't it?
We just
I
always
don't
say
think of mirror as
we
the
just
growth.
always say this cannot be the dominant mode because it's an order of magnitude weaker growing than the cyclotron mode at that point in phase space.
Well, mirror grows just when P curve minus P parallel over P curve is larger than 1 over beta. That's all you need.
Just and come back to this, what Stuart was saying, and you were saying about the phase angles as well, about propagation. So
Mhm.
this idea that maybe it's just mirrors don't move, whereas the cyclotrons get out of the way.
And that's why we think the mirror might, just from the simulations, the mirror just might be ultimately more effective at scattering the particles because it does not propagate. But
So an issue therefore is about the persistence of these regions. You know, so this is one thing that always worries me about what interests me about these plots is that you have all these dots on it, and like Stuart was showing that time series where actually the parameters change on relatively short time scales. Do you
Mhm.
have any idea, or is there any way of finding out
Mhm.
how long these extreme regions last? Is it that you just get a data point or two that are over there? Is it half an hour at a time? Is it a day?
well,
Is it
I have a Solar Wind 10 conference proceeding where we looked at the power spectrum of magnetic fluctuations over the course of the day as the plasma slowly rose in beta, and you could watch the different types of fluctuations developing and different things. So it depends. The nice thing about having 6 million data points is we can totally find you a 2-hour interval where it's sat at the same
But I
anisotropy.
mean, that's something that you could test?
Yeah,
You say
they tend to be very correlated within, one data point's correlated to another data point.
Can we go back to that? I want to say one more thing.
Yep.
I mean, a lot of the phenomena that I've been looking at lately, this velocity, the energy, that sort of thing, they seem to be enhanced above the cyclotron threshold.
Mm-hmm. But below the mirror, even
But-
though
but then
but they're
you run
shaped
out-
like
you
the
run out
mirror.
of data at the mirror.
Yeah,
So
yeah.
it seems like above the cyclotron threshold, you're doing
Stuff starts happening.
but it's not whatever it is.
Yep.
It's not.
I'd agree with that.
That's not
Could I say two things about it? So first of all, it may very well be that because the cyclotron instability wants us to have a cyclotron resonance, this is actually a very narrow band around cyclotron frequency. It may be difficult to decide if mirror is competing with it. The other thing is that you keep saying scattering particles, right? It's not actually clear that that's how this isotropization or this pinning of the pressure and of marginal stability happens. Because mirror, for example, right, has its maximum growth rate at both K parallel and K per I small.
Mm-hmm.
So it's a mu conserving instability largely. Right? So it doesn't actually have a lot of scattering mirror. If you take its fastest growing mode seriously. And the same incidentally is true about the parallel fibers. I don't know about the oblique. The oblique one probably does scatter. So However, that's not the only way that you can do it, because what you can do is you can change pressure and enthalpy by changing the fluctuation levels
Right.
of the magnetic field. Right, so this can be a completely new conserving process, and yet your P curve minus P power will change.
Do you know, is there literature that says that that is the case? That it could be that it does not happen by the temperature being, the thermal energy being redistributed from one direction to another? Because I think we have some evidence that that is
Yes,
what is
I
happening
write
here.
papers like this.
Yeah, I would like to, I've got a figure to show you in a little bit then. Okay, so I'm not going to get into this much detail as Stuart did. But it's been pointed out that just because the distribution of the data follows the growth rate contours is not like maybe it's necessary, might not even be necessary, but it's definitely not sufficient. So one thing Stuart's been working on is looking at the amplitude of magnetic fluctuations. I'm not going to get into that here. Just point out that indeed we do see enhanced magnetic fluctuations when we get to the edges of these distributions. And as Stuart alluded to. Up here, you tend to see more wave power when you're above the cyclotron instability. Is that because you're near the mirror instability threshold, or is it that you go above the cyclotron instability and something interesting starts happening?
So since that thought is up, I think I wanted to make this point earlier. Naively, one might think that since to scatter particles is a resonant phenomena that resonates with the cyclotron frequency, that you need very little power to do that. So it would be interesting to try to estimate how much power is required to scatter particles at the rate that's needed, and whether that's larger than or smaller than what you.
Doesn't Paul Kellogg have a paper where he looked at the amplitude of electric field?
That was just stochastic electric field
Okay.
scatter. It wasn't cyclotron.
Okay. Oh, that's a good idea. I'm going to skip this. All right, anisotropic proton heating. So there are a few examples of the heating processes happening in the solar wind. We can look at the individual distribution functions, and we see large perpendicular temperature anisotropies. As I alluded to before, in the corona, you have huge perpendicular anisotropies. As someone showed, I don't know if remember it was Milan or Tim, you look at the magnetic moment of protons as a function of distance from the sun, and instead of being flat, it actually increases with distance from the sun. These are all evocative that someone's dumping a little bit of extra energy in perpendicular to the magnetic field. And then I think we've seen bits of this before. So here's the distribution of data at 1 AU, but Lorenzo in the room there published this paper where he looked at data at 0.3, 0.9, and 1.5 to 2.5 AU, and you saw there was this evolution of where on this phase space plot the data were distributed. And a cool thing about this is if you just assume double adiabatic expansion, it should follow this line here, right? And it does not. And so one thing Lorenzo did in this paper is said, okay, well, how much statistically perpendicular heating do I have to put in? If I inject a little bit of perpendicular power, I can get the solar wind to follow this track instead. And so maybe what's happening is it's not following this track because it's undergoing a combination of double adiabatic expansion with a little bit, on average, perpendicular heating, and then eventually it gets here and it hits the fire hose instability and it gets pushed into this nozzle. The cool thing about being pushed in that nozzle, by the way, is this would imply that for any expanding magnetized astrophysical plasma, sooner or later, because of these double adiabatic expansion terms, you're going to wind up wedging the plasma in there, and then they will internally generate magnetic fluctuations. So we're interested in this stuff. Imagine a galaxy cluster, and you're wondering why there are so many fluctuations in the intercluster medium restricting the diffusion of cosmic rays. Maybe it's a phenomenon like this. Okay, but so if we really think there's some perpendicular heating happening to alter this trajectory, one thought is, well, why don't we look at the average temperature of the plasma here and see if we can find any evidence that the plasma has been heated anomalously higher to bring it up against that instability curve. So this was done the first time a few years ago in 2006. This is T-perp over T-parallel. This is beta, and this is the ratio of the temperature to the expected temperature ratio. Wasn't really completely clear if this was just some kind of beta association, but we have a new, more accurate version of our data set. And so this is now our first look with our new data set of the average temperature as a function of anisotropy and beta. And so what we find is indeed the plasma up here near the above the mirror instability threshold is several times hotter than the solar wind on average. We also find that the solar wind down here for T parallel greater than T perp is a little hotter on average. And what I'm going to do is skip ahead 2 plots, and then we can discuss this. So this is now looking at the perpendicular temperature on this plane and the parallel temperature on this plane. And so let me point out a couple things. The temperature enhancement up here is due to additional heating in the perpendicular direction. The temperature enhancement down here is apparently due to additional heating in the parallel direction. If it was just CGL that brought the plasma down here, it should be cooler in the perpendicular direction, not hotter in the parallel direction. So that's a bit of a surprise for us. Finally, let me also point out that it's not quite as clear in these plots because of the large range that they're following. But if you look at the parallel temperature up on this plane, when the perpendicular protons get very hot, the parallel temperature increases a little bit too when you're near the instability threshold. And T perp is actually a little bit elevated down here. And we think that's evidence that you can create a large temperature anisotropy, the instability starts to grow, and you wind up transferring some of the energy from one direction to the other. I have some, not in this talk, but I have some cross sections through this that make it a little more vivid. So that's why I'd like to talk more about this, because I think
it's just statistic. I mean, T perp is higher in
Yes.
the high part of the plot.
Yes.
And,
yes, absolutely.
And T parallel is
Absolutely.
higher at the right-hand side of the plot.
Absolutely.
Combined with temperature generally being higher, that
Yeah, so you could ask, like, for instance, if beta parallel sure should be proportional to T parallel, right? And so I would expect the temperature to generally increase as beta parallel increase, T parallel should increase, right? And likewise, R is the ratio of T perp over T parallel. So you can ask yourself what contours you would expect to observe if those were just the dependencies. And let me just a couple points of rebuttal. First of all, if you look closely in this track at isotropy, that's where the minimum occurs in temperature. So if I cut through this at any of these points, what I find is the minimum temperature is at isotropy, and then it increases out in either direction, the total temperature. We do not have what you would expect to see if it was just T perp over T parallel and then beta proportional to T parallel. If I go back to the components, what you expect to see is T parallel would be ordered like this, right? And indeed, over here, where we're far away from the fire hose instability, we do appear to see kind of this kind of dependence, which is consistent with what you might expect if there was just a beta parallel dependence. But when we look at the contours here in the temperature, they seem to be more dependent on where they lie relative to the growth rate contour than just what beta parallel is. And for T perp, it's actually more dramatic. If you just thought it was an anisotropy dependence, the slope would be very different. But what we would really like to do, and Stuart alluded to this, is I'd be happiest if we took all the data and like ordered it by growth rate instead of where they are on this plot, and we'll look and see if the temperature is even more clearly associated with the growth rates.
How does this relate to Lorenzo's plot of where he's giving it a little bit of perpendicular energy?
Yeah,
He's
well,
giving it perpendicular heating.
so I mean, this is completely consistent with that,
How about another second?
right? But this is not.
Exactly.
So I mean, we do have a big problem here. That it's the plasma with T parallel greater than T perp and high beta parallel appears to be significantly hotter in the parallel direction. And this is a log scale, and the typical solar wind is maybe 100,000 degrees, and this stuff is about 600,000 degrees on average. Now, the other thing that's, I won't get into the details about the theory, but there are plenty of theories that say, I dissipate this and it preferentially dumps energy in the parallel direction, or preferentially dumps energy in the perpendicular direction. So something about this that has us a little bemused is we kind of thought that, you know, we'd get above beta of 1, and suddenly, instead of things being hotter on this side, they'd be hotter on that side. Be like, ah, yes, you know, there's a beta dependence on which dissipation mechanism is dominant. But like I said, if I draw a cross-section here, I see a little parabola with the minimum temperature at isotropy and apparently signatures of heating on both sides.
So it's just anti-correlated with collisions.
No, this is all collisionless data. Yeah, we removed the collisional data from this. Okay, I'm going to show you one more thing, and then I will stop. And that is relative heating of helium to hydrogen. So equal temperatures, 4 times the temperature, supermass proportional temperatures. And how does that arise? So again, there are a lot of different very compelling theories. But one idea that we have in the solar wind is focusing on absorption of alphane cyclotron fluctuations in a plasma with multiple species. So what you want to imagine is a whole spectrum of alphane waves are traveling along. So in this plot, this is speeds perpendicular to the magnetic field. Here's speeds parallel to the magnetic field. And so I have alphane waves moving along. And a particle could scatter off the wave. And in a frame moving with the wave, it'll just slowly rotate around in a circle. In the frame of view of the plasma, what that winds up turning into is additional heating in the perpendicular direction. The interesting thing about this is heavier ions will actually resonate with slightly faster waves. So it is actually possible in some versions of these theories that you wind up with this mass proportional heating in the perpendicular direction. So what can we do to test for these kinds of theories? Well, one way to do it is to look at what would happen with a 2-species plasma. So the key thing is that the relative heating of these different species can be regulated by the differential flow between the species. So imagine a case where you have protons and alphas moving along at the same velocity, some spectrum of alphane waves flowing along. All right? If they're moving at the same speed because of their different charge to mass ratios, the alphas are going to want to come into resonance first, and so they should be heated perpendicular to the magnetic field. But what people have realized is alphas can actually stream up to the local alphane speed. And so if the alphas are moving fast enough, they'll come out of resonance with those alphane waves. And what you should see instead of a large alpha temperature anisotropy is maybe a proton temperature anisotropy, or at least more heating of the protons than of the alphas. All right, so the prediction is that for small differential flow relative to the alphane speed, actually it's around 0.15, so 15% of the alphane speed is when the transition should happen. Helium should have a stronger cyclotron resonance than hydrogen and be heated faster. On the other hand, if we increase the differential flow enough, they should come out of resonance. So this is just another example of the kind of work we're able to do. We're looking at the perpendicular alpha to proton temperature ratio as a function of 2 parameters. The differential flow, that's what we're interested in. But here I have the collisional age. So remember, we've shown you that a lot of things are also a function of the collisional age. So this is a lot like the working group on analyzing different dependencies in tokamaks. You've got to sit there and think really hard about, when I adjust this, what other parameters are changing? Am I factoring that in correctly? And what we find is the most important thing is if you turn up the collision rate, you just get equal temperatures. And you also tend to have smaller differential flows. And we didn't want that effect to drown out our analysis. What you do is, focus on one narrow range of collisional age, preferably low collisions. And what happens when we look here is you see that when the differential flow between the species is small, the alphas are very hot, on average about 6 times the proton temperature. And then as the differential flow increases, the temperature of the alphas drops off. You can see even up here where there's a very high collision rate, at the lowest differential flows, the alpha temperature turns up just a little bit. And so we interpret that as even when there are a lot of Coulomb collisions and they quickly thermalize the 2 distributions, if there's any wave power getting absorbed and there's small differential flow, the alphas will soak it up faster. Okay, and then one last thing, if I just look now at all the data in this narrow range of collisional age, at the temperature anisotropy as a function of differential flow, red is for the alphas, blue is for the protons. And what you indeed see is when you come down below differential flow about 15%, not only are the alphas very hot, but here's where the alpha perpendicular anisotropy really takes off. So we think this is a very compelling evidence for this alphane cyclotron resonant interaction happening in the solar wind. And it's just really interesting to see how, depending on a factor like the differential flow, you can regulate which species soaks up the fluctuations. So I think I'm going to skip a couple words about electrons and just, like Stuart said, the next really exciting thing for us is hopefully these solar probe and solar orbiter missions going into the inner heliosphere. They have really good plasma packages. We can get in, we can look at very different betas, higher electron and ion temperatures. I think there's really a lot of exciting stuff to do there. Okay, so I'll just put up my conclusions and take any questions.
Right, Justin. Okay, any more questions?
So about the last one about the collision light. So that is for ion-electron collisions, is that right?
I'm just using, for simplicity, the proton collision timescale.
Okay,
In theory, I should recalculate probably an alpha proton collision.
Right. I was just wondering how different that was.
Yeah,
Okay.
yeah.
Okay.
And
if it's proton, I guess it's probably not that different.
It's not that different. The electron stuff I didn't show you. We've started now looking into relative heating of protons and electrons in the solar wind, and there the knobs we can turn are the proton-electron Coulomb collision frequency, and then other things.
Questions? Well, okay, yeah, Mr. George. George?
This is kind of a silly, ignorant question, really. So you've shown these spectra, broadband spectra, and its breakpoint around k rho I of 1 or so, or some of you have. Not you earlier. I'm just trying to connect them here. Then you talk about these instabilities. Are these directly connected, like these cyclotron or these fire hose instabilities?
Yeah, I mean, what we really want to. So what we're trying to get our head around now is, if you're studying turbulence, what you tend to do is take a time series where the spacecraft seems to be working well, and I've got continuous data, and okay, now I'll Fourier transform that and see what happens. And what we're realizing looking at this stuff is, at any instant, if the protons or the electrons, veer into one of these unstable regions, they'll generate fluctuations locally that could definitely interfere with your interpretation of the observation. So one thought is we need to maybe find some pristine data sitting in the center of our distributions here where nothing appears to be unstable. But it comes against a big question, which is once the plasma goes unstable and generates these fluctuations, how long do they persist within that volume? Could that piece of plasma 10 hours ago or a day ago have been unstable, generated large amplitude fluctuations, and those fluctuations are frozen in, or have they drifted out? And we're just starting to try and come to terms with that. What I'd love to see is power spectrum as a function of location on these different plots, and Stuart's working on it.
Yeah, I think it's very doable.
Well, it seems like, if we believe that little bump in the spectrum of magnetic field that Tim showed in his talk from Rob Wicks's paper, right, that is the signature of the fire. What it says is that you will only see these things in the parallel spectrum, not in the perpendicular one. It also suggests that actually the signature on the spectrum is not terribly big, right? Because
that was a long interval high speed solar wind, where actually it's not strongly unstable. I guess it's kind of gently bumping against it. So
I think we
that's a
could do
little
that. That
weakness
goes back
for
to Bill's question and Greg's question. And I think we have enough data that we could actually find. I didn't show a plot, but if you look at the times when you have E aligned with B, and in that wind data set, there's
Oh, the one with the
Must
huge
thousands of
fluctuations.
50,000 intervals or something like that.
Yeah.
So we probably can actually make a sample of that.
yeah.
But
You've got enough. You can cut it any way you like.
well, but this is a lot of work. That means you have to write 50,000 Rob Wicks papers for
No, the thing is you don't. No. Because you're doing this.
Work.
Remember, what Robert was doing was actually looking at the MHD inertial range, right? This blip was a surprise. It wasn't what we were looking for. If you're looking at those higher frequencies, you actually only need very short intervals of data. You can do it with do it with, let's say, 5-minute intervals, and just see
so
how
now
they
you
move
have
around.
to color your plot according to the blitz.
Yeah, I mean, what we'll do is we'll make spectra. We'll scale the spectra and try to
Yeah.
what the spectra
I mean,
is.
we've already shown with fluctuations at 3 seconds, whatever that means physically, there's a strong enhancement of the wave power along the fire hose instability threshold. So we know at 3 seconds you get much stronger fluctuations than you typically do in the solar wind along these curves, which doesn't make sense, maybe. But what we really
I
want to
think
do
it's
is look at the
very
power
good.
spectrum and
Yeah.
you know.
So there is
That's
another
very
issue,
doable.
right? This injection of energy by these instabilities doesn't have to be at that specific scale, because basically the scale at which the parallel buckets injects energy depends on how close you are to the threshold. And if you are very close to the threshold, that scale can be much longer than drawing. And the same, I think, applies to mirror. So actually, that injection can be all over the place, and it can very easily be at much longer scales.
So that would be an interesting thing to look at.
Yeah.
Over enhancements of power as a function of K rho.
So I mean, if you had good statistics of spectra depending on how close they are to the threshold,
Yep.
that would be fascinating.
Yep. Yeah, and right now we've just got this 3-second fluctuation parameter, but that's definitely the next step.
Well, there's I have spectra now too. Velocity, we have a good spectra.
Might it be more apparent? I mean, you talk about measuring electric field, and we agree getting more fields is better, but maybe temperature fluctuations, would that be, if you can measure it with better instruments, maybe that's a way to pick these things out relative to the rest of the spectrum.
One issue is we only get a really tight temperature measurement every 90 seconds.
I know, but I'm thinking about future missions
We
maybe.
have a proton temperature measurement.
Oh, that's true.
And I mean, I have a tensor. I have the pressure tensor.
Yeah. But I mean, our temperature uncertainties are like 10%. So you'd have to ask what level of the
Right.
But on the other hand, you
amplitude
do see
fluctuations are.
a power law temperature distribution. I mean, as a function of frequency out to where it starts to hit the Poisson phase.
I'm conscious of the time. Are there any other questions? Okay, good, thank you. I thought they were both excellent talks, and hopefully that's given the kind of tokamak community some idea about the kind of measurements that can be made in the solar wind and the kind of detailed analysis that can be done. And talk to Stuart and Justin if there's things that this meeting is about, the crossover between the two communities. So, and they're giving you a good idea about what's possible. Maybe we can help the tokamak community as well. Okay, thank you. Coffee now, and we're back at 11:30 for Thierry's talk.